PM substance assessment for as many chemicals as we can, given the amount of data we have. So this is a big caveat. I will also add that we have a discussion cafe coming up right after the following presentation after mine, so Emma Palm is going to present a bit, and we have a discussion cafe focusing on uncertainty. So really looking forward to that. We've already had some really good comments about this. So just to start, this is all old information for everyone now. PMT, we're talking about persistent mobile toxic, or BPBM, very persistent, very mobile. So specifically for mobility, we're talking about using KOC, so potential for a chemical to enter groundwater, and spread over long distances to contaminate drinking water. This we often characterize with the organic carbon-water ratio. It has units, it's a concentration ratio. That's, I think, sufficient for now. For persistency, we use half-lives. It's a potential for a chemical to degrade quickly in the environment. Sometimes we have ready biodegradability results, which are binary, indicates if a substance is not P. And you also have phase-specific thresholds based on degradation half-lives. So at 50%, when 50% of the chemical has disappeared, what is the time? That's the half-life. Usually this is reported in days. So there's some challenges that people have already hinted at when we're talking about classification. So I'm working with a data set based on Raoul's data that includes 380,000 substances. It's a lot of substances. Most don't have data. And most especially do not have measured data. So how do we go about handling this is what I'm going to be talking about. So as I mentioned, I'm focused mostly on KOC and half-lives, PM, classification or thresholds. These are environmentally dependent variables, so they have differences in pH, temperature, soil type, concentration sometimes. Maybe the concentration or like the composition of the bacteria present changes the way that persistence can be measured. The presence or absence of other chemicals and reactants can affect this. So a lot of competing factors, very hard to quantify. And especially if you don't have all this metadata, how do you compare data? How do you combine data for different chemicals? So this is an example of KOC. These are 4 different chemicals. You have log KOC on the bottom of this axis. The points here represent reported data for KOC for the same chemicals. And you can see some of them span orders of magnitude. Some of them might be classified as M in some cases. If you use one data point, maybe they're not M if you use another data point for the exact same chemical. So some of the data is also considered censored, so it's above, below, or between 2 values. And so you can't really take the average of these kind of data points. So we're working with a lot of complex data, a lot of chemicals. But as Raoul mentioned, we're also working with inches, because that's how we've standardized things. But inches have a limited amount of data as well. So this is atrazine, this is the structure based on this inchi, but you can also have these structures. And these are all atrazine. And atrazine then has 5 different smiles that can be entered into different Q subs and give you different KOC predictions, different persistency predictions, different ready biodegradability predictions. They're not supposed to, right? Ideally, you get the same chemical in, you get the same result every single time, but because of the way that models work and the way that they're parameterized based on, maybe it's based on chemical fingerprints, maybe it's based on functional groups, it does end up giving you different predictions. The best way would ideally be to have experimental results, because then you actually get the experimental result is probably a result for the mixture of tautomers, right? Not for a single tautomer itself, because that's how they would naturally occur in the environment. But it's just something important to consider when we're dealing with so much data, and because I'm working with inches, I don't know what the ideal smiles are going to be, and there's no real good way to kind of identify this. So I am going to be working with tautomers, and I'll talk a little bit more about this later. So I start with about 380,000 chemicals on the global chemical inventory. I separate and identify the unique ones as well. So this reduces them back down to 280,000 that I'm working with now. I then remove inorganics and isotopic information, so labeled carbon, removing that. they're considered separate in the inventory for now. I also remove all organometallics because QSARs will not work for these. And then I also calculate the tautomers. So for all of these 233 substances, I end up with 36 million smiles. It's a lot of smiles. I cannot run all the models that I want to run on 36 million smiles, so I have to do some work to reduce it. So I first reduce by doing a size category. I'm only concerned with chemicals smaller than 1,000 grams per mole. When I do this, I get rid of quite a bit. About 200 substances account for more than, have more than 1,000 tautomers. These are generally because they're very large, they have lots of nitrogens, so the bonds move around quite a bit, so makes sense. And then I decided, okay, let's try to bring it down a bit more. 500,000 is still quite a bit, so we got it down to about 300 by filtering for substances that are less than 500 grams per mole. And then we still have some chemicals with lots of tautomers, so I'm like, okay, I'm going to say I can sample a maximum of 5 tautomers per chemical. That's my cutoff. I went with this, and then to reduce it even further, we decided only to focus on 0PM substances. That still leaves us with 120,000 smiles to work with. So it's a lot of data. So this is my simplified workflow for doing an M assessment. So I start with all these smiles. For example, I run a model like opera. I end up with a single KOC for opera. Again, specific case for opera. And then for each substance, I run a Bayesian analysis approach to get a probability distribution for the KOC. And then this is per substance. So if a chemical has 5 tautomers, I actually combine all 5 tautomers and get a probability distribution. Most of the time, they might be similar, but there is some variation that occurs. I then end up, or the goal is to end up with KOC values for 93,000 substances. I do this now for a lot of different models. So I have 6 different models here, different parameters, different applicability domains. I take this all into account. I also take into account weighting based on this. I then get a different number of smiles for each. So for example, with ACD Labs and Franco equations, I can actually parameterize these with pH, so great for ionizables. So I run them at different pHs because, as I will get to when I combine it with experimental data, I do not know what pH this experimental data is. So I'm taking the range, so I have a distribution. EpiSuite gives me 2, so with all of this, I now have a distribution for every substance, for every model. So lots of distributions. And so this is 93,000 substances with about 6 distributions each. So a lot of data still. But I can take this data, I have experimental data that I've collected from different sources that I trust as being reliable. Not an intensive literature search, I'm sure there's way more data out there, but a limited set collection of pre-assessed KOC data, I would say. I also take regulatory data. So this is data from eChem portal or OECD QSAR toolbox. I keep this separate because it is very difficult to actually identify what data that is listed on the regulatory dossiers is experimental or estimated without actually going and looking and reading the dossiers. I don't have that much time for this postdoc, so it's not such a feasible endeavor to actually pull experimental data specifically from regulatory data. So I just categorize it on its own, slightly lower weight than the experimental data. I then have all the estimated values. Again, give it a lower weight, but now I have estimated values from a lot of different sources, different models that are parameterized different ways, and work in different ways. I then, finally, get a probability distribution of the KOC per chemical. This is now useful. This is information that we can use for this PM assessment. What's interesting with distribution, though, as you can see, it is a curve. So it has minimum, maximum, take the average, pick the mean. You can pick your like choice of endpoint, really. So it really is a choice that you have to make based on what risk adverse or how risk averse you want to be. So here is some of the distributions that we see. And so to walk you through this, we have 3 different plots. On the left, we have the minimum. If we use the minimum of every distribution, This is the range of KOC values for the chemicals in the global chemical inventory. The middle is using the average value, and the right shows you if you use the maximum. See, it's quite different, and so it's really interesting to kind of see how this variation occurs. That being said, probably will never, there's no need to use the minimum and maximum. It's just an interesting example. It looks really cool, I think, when you visualize it this way, because I cannot show you 93,000 plots. But as I mentioned, you can kind of use different types of endpoints. So I have here different percentiles on the bottom. So if you use the 90th percentile or the 25th, you could perhaps arbitrarily choose something based on how risk averse you want to be. I say arbitrary because there is no real way to kind of decide what is a good threshold. That is something for regulators to decide. So for me, median and mean, pretty good central tendency indicators. They tend to, they show the middle. So good endpoint, I think, for our use case. And for our example, so these are the values that we will be using when we kind of upload it all and link it all into the OWL's work. The raw data as well, we will try to include as much as we can eventually on GitHub and with the publications once we have it. All right, so now on to P. Okay. So I said there are different ways of getting P data. You have ready biodegradability tests. Gives you 1, it's ready biodegradable, or 0, not ready biodegradable. Doesn't give you a lot more information than that. So we can say it's either not P or VP. We have no idea. And this is not guaranteed, it's just testing in a setting, but we take what information we have. The other data is phase-specific thresholds based on half-life. Then we can actually compare the half-life to regulations and then categorize things as not P, or VP. So 2 very different types of data. How do we combine this? So again, still working with 120,000 smiles. I, again, go to my models. I'm using Opera. Opera has RVD data. So this is binary data, 1 or 0. Is it persistent or not? So for this, I can do something of a probability distribution, get a probability based on all of the smiles and all of the RVD data that I provided for the same chemical, and what is basically the likelihood that a chemical is persistent. That's what I get out of this. Simplified in this plot here. And so I can do this for 93 substances, 93,000 substances. EpiSuite also does predictions. So EpiSuite has BioWin. BioWin gives you a lot of data. I've used the consensus value for this one that they provide based on, I think, BioWin 3 and 5. Also, Opera, completely separate model, like the training data is separate, so I included this as a separate model, which predicts the log 10 half-life in days. So these are slightly different models, but I can get a probability distribution for all of them. So keep in mind here, these 2 are probability distributions of P, not P. And this is a probability distribution of, is it not P, P, or BP? So I also have experimental and regulatory data now, and I can combine it with all the estimated data, which is nice. And I can get a probability, again, of a chemical being not P, P, and VP, using some maths to kind of combine that weird thing with the RB and the half-life data. So this is an example of a chemical. So you can see this chemical would be considered not P here, with this in the green here. And this chemical has a very low chance of being VP and a very low chance of being P, which is P is shown in yellow, VP is in the red. On the other hand, this chemical, as an example, I have not pulled the chemical identities from this data set, so we're working with real chemicals but unidentified. This chemical has a very low chance of being not P, and pretty good chance of being P, but most likely it's going to be VP with the red here. So we've kind of categorized it in 2 and a half ones. So this is a subset of our data that is a chemical, or the probability of a chemical not being P. So this is the chance of all the chemicals in the database not being P. So this includes chemicals that are persistent. They're just going to be showing up down here because they have a very low chance of not being P. Chemicals that are very likely to be persistent are going to be above 50%. So this shows you a lot of chemicals here have a probability higher than 50%. This is the opposite. So this is the probability of all the chemicals in the subset of 32,000 being P. So interesting way of the distributions are sort of laying out. And so in this example, this includes either being P or V. So what's next? So the P assessment of the remaining substances based on the available data will be also extracted. There is an upcoming seminar to show how to use the database once we link my work with Raoul's work, and how to actually pull and extract the PM information. There will also be a ZeroPM pieces a little later in the year that's going to be published to the YouTube, specifically about the M approach and all the details relating to that. So with that, I want to say thank you also to our colleague from NGI who's helped a lot with the Bayesian statistics and the computational facilities. Thank you.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.